So today we're going to talk about the application of reflections and rotations, and that shows up in symmetry. So symmetry is where something is the same as it was originally, or it looks the same. It appears to be the same after it has undergone a transformation. So line or reflectional symmetry is a reflection that maps the new figure. The new figure is mapped onto the original figure. What that means is basically it looks the same on both sides. Okay, so the reflection maps onto itself. You can imagine folding along the line of symmetry or the line of reflection, and everything on both sides matches up. Kind of like a butterfly, how if you fold that butterfly in the middle along its body, if you use its body as the line of reflection, then it's the same on both sides. That is a line or reflectional symmetry. Rotational symmetry is a rotation that maps onto itself. And all I mean by maps onto itself is that once you change it, it looks the same as it did before. You can hardly tell that it is any different. So a rotation would be that it rotates about a point or a center, the center of rotation, but it looks just the same as it did before. And where this is affected is a regular polygon. So if you ever see something that's referred to as a regular polygon, what that means is that all sides and angles are congruent to each other. All sides are congruent and all angles are congruent. Not that the sides and angles are congruent to each other, but that all the sides are congruent and all of the angles are congruent. So let's look first at line symmetry or reflectional symmetry. How many lines of symmetry does each figure have? So you can imagine folding this rectangle. It's like a piece of paper. We can fold a piece of paper in half like a hamburger fold, or we can fold it in half like a hot dog fold. But we cannot fold it in half along the diagonal. If you try to fold a piece of paper in half across the diagonal, it doesn't map onto itself. It doesn't match. So those are the two. It has two lines of symmetry for a rectangle. Now this is a regular pentagon. If you look at B, it's a regular pentagon, which C is a pentagon also, but it isn't regular. The difference is that in B, all of the sides are the same and all of the angles are the same. Okay, what that does is it creates, then we've got this line of symmetry here, this line of symmetry here, and we can fold this pentagon in all these different ways so that we have 1, 2, 3, 4, 5 lines of symmetry. Now with this other one, with this other pentagon, the only line of symmetry that we have is that one. And the difference is because the regular pentagon has all the same side lengths and all the same angle measures. And so that's what makes the difference in creating those lines of symmetry. So now rotational symmetry, if you can imagine this figure rotating, so kind of like a pinwheel, if you stuck a pin in the middle and you rotated it around, could you make it look like it does originally? Well, so one way to look at it would be to divide it into pieces. So if you go from the center to each of the pieces that match, so each of these match, you would have 1, 2, 3, 4 pieces. Now what we're dividing into pieces is if I went all the way around, that's 360 degrees. So what we're doing is we're dividing 360 degrees into 4 pieces. So our rotational symmetry would be 360 divided by 4, which is 90 degrees. So this square has 90-degree rotational symmetry. If I rotate this corner right here around to that corner right there, I wouldn't even be able to tell that it looks any different than it did originally. It would just look exactly like it started. We can do the same thing with this hexagon. If I go in and put that center point and then connect all of those vertices where they look exactly the same, then I can count around. I also like to show students too, you can do this. If you go from vertex to vertex, matching vertex to vertex, there's 1, 2, 3, 4, 5, 6. So whichever way makes the most sense to you. But we're going to take 360 degrees, we're going to divide it by 6, and we find out that this hexagon, this regular hexagon, has 60 degrees of rotational symmetry. Now this kite, though, there are no points that are the same. If I rotate this kite at all, you can imagine if you stuck a point here in the middle, a pin, and you tried to rotate it around, you would have to rotate this point all the way around before it looked like it does right now. And there's not 360-degree rotational symmetry. So if it's more than 300, if it's 360 degrees or more, then it has no symmetry. So this one has no rotational symmetry. So let's look at some examples. Let's decide, do they have reflectional symmetry? Because sometimes you can be reflectional and rotationally symmetric. So does it have reflectional symmetry or rotational symmetry or both? If it has reflectional symmetry, we're going to draw in the lines. If it has rotational symmetry, we're going to determine what degree of rotation it has. So if we look at this snowflake has this line here. So once you find one, you can find some other ones. So that splits it in half, that one splits it in half, that one splits it in half. But don't forget to also look for these other ones. You can fold it also directly down one line. So we also have those. So obviously it has reflectional symmetry. It has those 6 lines of reflectional, actually 1, 2, 3, 4, 5, 6, yes, 6 lines of reflectional symmetry. And so the question is then, does it have rotational symmetry? Now, when you rotate it, you're going to have to rotate it from this piece to this piece, right? You have to rotate from this point to this point. So we have 1, 2, 3, 4, 5, 6. If you can rotate it once, then you can figure out how many times could you rotate it. So yes, it has rotational symmetry. It's 360 degrees divided into 6 equal pieces, so it has 60-degree rotational symmetry. Okay, so if we look at this shape, it has these 3 arms. There's no way to split this in half. Imagine folding the paper along a line. Nowhere is it going to map onto itself, so it does not have reflectional symmetry. So the question is, does it have rotational symmetry? Well, if I take this point right here and rotate it around, it will match up with that point right there. You can also look, if we connect them like this, I can connect each of those matching points. So I have 1, 2, 3 pieces. So yes, it has rotational symmetry. I take that 360 degrees and divide it into 3. It has 120-degree rotational symmetry. If we look at this shape, number 5, does it have reflectional symmetry? Can you fold it in half so that it maps onto itself? Yes, I can fold it that way so that it maps onto itself. I can also fold it vertically and it folds onto itself. So yes, it has reflectional symmetry with those 2 lines of symmetry. Does it have rotational symmetry? So we look for similarities. So if I were to take this center point and this center point, I could rotate it around. Think about an hourglass. I could rotate it around and it will look exactly like it did before. I can rotate it twice. I have 2 turns. So those 360 divided by 2 turns, I can rotate it 180 degrees and it will look exactly like it did before. So number 6, reflectional symmetry. So we look, can we split it in half? Yes, I can fold it there, but don't forget, we also have these diagonals. Always look for the diagonals too. If you fold those up, then they'll match up. So I have those 4 lines of reflectional symmetry, and then I check, do I have points that will, when I rotate them around, they'll match? Yes, if I map each of these arrows onto itself, then I can take 360 degrees, divide that by 4, and find out that it has 90-degree rotational symmetry. So I have this 5-pointed star. So does it have reflectional symmetry? Can I cut it in half? Yes. 2, 3, 4, 5. Once you find one, find all the ones that are similar. So yes, it has reflectional symmetry. Does it have rotational symmetry? Imagine if you took this point right here and you rotated the star. If I rotated this point to this location here, it would look exactly like it does now. So I can do 1, 2, 3, 4, 5. Now notice that I am not going from line of symmetry, not 70, 72, sorry. I'm not going from line of symmetry to line of symmetry. I'm not going from here to here, right? That would put this point right here, and then it's not symmetric. It doesn't look like it does right now. So you're not necessarily going from line of symmetry to line of symmetry. You've got to look at from point to point. Okay, so if you look at this last figure, if you reflect it, there's no way to fold this so that it folds on top of itself. So no, it does not have reflectional symmetry. But if I rotate it, so if I take this little pinwheel thing and I rotate it from here to here, then it matches up. And so I can rotate it around. And if I go all the way around, there are 12 different star tips. And so I can take 360 and divide it into 12 pieces and find out that yes, this has 30-degree rotational symmetry. So you're looking for, with reflectional symmetry, you're looking to be able to fold it along an axis and have it map onto itself because it's a reflection of itself. Or you're looking for a rotation to be able to rotate it so that it maps onto itself, so that it looks just like it did before you ever turned it.